Do you imagine what happens when a syntactic foam is subjected to a pure shear deformation? This is what I'm going to show you in this video of how these syntactic foam structures deform when they are subjected to a pure shear deformation, so that you get results that look like this, and like this. If you're interested in this, then sit back and relax as I show you how to do precisely this. So welcome to this video. There are 3 steps that you need to follow in order to apply this pure shear deformation on a syntactic foam. And the first step is to actually create the geometry, which is generation of vector domain. And then the second step is the nitty-gritty of the steps required for imposing the pure shear on the structure. And we're looking at this in terms of the XY, the YZ, and ZX shear planes. And then finally, the third step is how to actually extract the stress strain data that will help you now generate the effective properties of this material. So now for the first step, which is generation of virtual domain, I've already made a video where I showed in detail of how to do this. So if you really want to work with me with the model that I'm going to be working with, please look in the download section. You can download a version of this for you to start working with me. Or if you want to actually do it yourself, then this is the video that actually tells you how to go about doing that. So in terms of the geometry, we're not going to do that. So the second step is how do you actually apply the loading history that will impose pure shear, and I do it in really very unique and interesting way, and that's what I'm going to show you. So let's get into ABAQUS. So here we are in ABAQUS. This is a model that we're working with that you can download. Once you get a version of this code, that's what it looks like. And if you look inside, so the first thing, you go to the part module, and within the part module there already is a complete version which is called the Syntactic RVE. And we're going to put the syntactic RVE, which is the representative volume element, which is precisely what we see here. So if you look at there's the part that we're working with here. So there are a few things that we're going to do. So the first thing we'll do is to explore meshing this model. So if you double click there, and it's giving me a mesh of about 6. I'm okay with that. Then I'll select all of that and associate it with a tetrahedron. Tetrahedron normally will work well for this structure. So we need the meshing tool, which is the very first one here. So if you select that, and that gives us a mesh model that we're working with. So if I switch this to the material model, so it looks okay, and we have a good structure that we're going to work with. So then the next thing we're going to do is the materials that are being created. So working with an epoxy structure. So the properties are given here. Again, if you look in the link, you will see a link to the paper that I'm using in working on this video. So look at that. And the microspheres are also there. The properties are also given here for you to use. Now, after you've done all that, so we create the sections. So we've done all the sections for the top for both of them, and we can then go to this section, and under the section assignment we can assign the section that is the sphere and assign the section which is also the epoxy. So we're happy with all of that. So the next thing is look at the assembly module. So within the assembly module, what we need to do is to create certain sets. So we're going to just go into the assembly module under the set. So I'm going to have my X front. And what would that mean? So I'll need to go to the top here and select, okay, I want the faces selected, and I want that done by face angle. So if we hover here, it will select that face. Then I can do Y top. So I'll hover on the top, and then I'll create the set for the top. And then Z front, I'll hover around here and select everything for the front. And then I'm just going to rotate the system so that I can also create set for the back as well. So we'll do the same. So I'm going to have my X back. So what would that be? So this is a X-axis. The back end of the X-axis is there. So this is fine. And then Y base. So this is the Y-axis. The bottom of the Y base is there. And then we have the Z back. So Z back, which is the one that is on this end, back of this Z-axis. So that gives us everything. So if we look at the default here and go into sets, okay, so we've got all the set specified properly. So the other thing we then need to do is introduce 2 reference points that we're going to use to apply load on the structure. So the first thing is to probe. So if I probe here and find 2 corners, so I'll press down shift, select that, and select the other point. So we've got 2 points that we need, and then that will identify the reference point. So we'll pick up the first one. So that will be my first reference point. So I'll go and create a reference point and put that coordinate. I'm going to make it a little bit away from the X on the X-axis, so it becomes a point there. So I'm going to also take the second reference point that we need to create, and paste it in that environment, and I'm going to make it a little bit up as well, 90. So we've got 2 reference points, which we then have to create a set. So I'm going to call my reference point set 1, which is for this first point. So we select what, so we need to switch this to all again and then select everything. That's okay. And then we do the same thing. I've got reference point set 2. So hover around that, and that gives you what you need. So we've got it all created, the reference point and all that. So let's create a loading step. So I'll call this loading step. A static general for a start should be appropriate for this. And we look at a history output. So reference point history output number 1. So that will be based on the set on just the reference point number 1. So I could ask it to give me RF1, RF2, RF3, U1, U2, U3. So we're going to work with that, but we're going to change that depending on what we're trying to do. So I'll also do the same reference point history output 2, and that will be based on a set attached to number 2, RF1, RF2, RF3, reaction forces, and then displacement 1, displacement 2, displacement 3. They're all correct. So we can then think about how do you apply the boundary conditions. So we've got the first model here called shear. So we're going to shear on these 2 planes. So what we need to do is I will shear on this point and that point. So I need 2 loads to do that for me. So I'm going to call my XY load. So the XY load boundary condition, and that will be associated with a reference point at number 1. And the system is going to shear in the Y direction. So I could say 30 is what I want. So the system is 80 millimeter, 80 micron in length. So if you make 30, so it's shearing up on the system. So we need to do the same to shear horizontally there. So I'm going to call that my ZYX load. And that will be on reference point 2, and it will shear in the X direction still by the value of 30. So this is what we get based on the shear on those 2 cases, and this is fine. We now need to link it to the face of interest. So we need to link what's happening here to there, and that's where our constraint equation comes in. So I'm going to have constraint for 1. So let's call it for reference point 1 and the star equation. So what we are going to do here is 1, and it's linked to the front face of the X front. And we're moving into 2 directions with reference point 1 and -1. So this way we have constrained what's happening here to that face, and we'll create a constraint 2. And this would again be 1. We are working now with the Y top in the X direction, which is 1 direction, reference point 2, and -1. If you want to learn a little bit around how I'm going about creating this reference point, then look at this video where I explain in detail of how to actually set up this model. Okay, so we have this constraint to that. So the other thing is that we need just 2 types of boundary conditions. So because we are working on the XY plane, so our boundary condition would have to be, there will be an X back boundary because we are applying the load on the front, and the back will have to be fixed. So I'm going to find an X back initial boundary condition. So say boundary condition, and we are going to apply it on the back. Okay, and how would the system be deformed? So we are going to constrain it so that the back will be constrained in the 2 and 3 direction, because if you think about this back end, so we are going to deform the top in the X direction using the second load, so that end will need to be moving in the X direction. So the degree of freedom in the 1 direction will be free, so we've constrained that. So we then do the same thing Y base, because that's the second thing. Remember, we are doing a shear load of XY plane, so there will be X and Y boundary conditions, so BC. So now this time around we apply it on the Y base, can highlight that. And so this, again, because you're going to move this in the Y direction, so 1 and 3 will be what you're working with, because for this base to deform, it's going to move in this front in the Y direction, so 2 will be free. So that when you combine both of them, the line that is around here will constrain in the X, Y, and Z direction, and so it basically becomes the anchor point, and this will be the 2 planes that are moving in shear. So that's what we're going to do with the system, and we have it all set up properly as it's supposed to be. So if we then go back to the material model, we're happy with the material and everything is fine, and we can then create the job. So that's the name of my job, and we're happy with that. So we will just go back and do the same. So I'll create other copy. So if I copy this time around, we have to be the YZ plane. So with the YZ plane, everything remains the way it is. There are a few things that we need to change. So the first thing we change is the load. So the first load we have here would be the YZ load. Okay, so YZ load. So where would the YZ load and ZY load? So the other one will become a ZY load. Okay, so let's get the YZ load. So YZ load, which is this. So clearly with the YZ load, as we apply the system here, it's going to deform what's happening at the top on that face. Okay, so this first case will cause a YZ. So this is the plane of Z, and you're deforming towards the Z direction. So that means I'm really interested in what's happening towards the Z direction, because it's a YZ plane. So on the plane, and this would be linked to the top surface, which we are going to do in a moment. And then the other one, which is ZY load, means that you're moving in the Y direction. The plane is Z, however, the Y, ZY. So that's why we have that. So we've got those two, this and that. So we now need to link them to the appropriate. So the constraint 1, which is the constraint linked to this, we need to move it to the top. So remember, it's YZ, so it's Y top. And it's moving in the third direction. In the third direction, it's linked to reference point 1. So what have we done? So we're applying a load here, and it is applied on this point in the Z direction. So what about constraint 2? So if we look at constraint 2, this time is the ZY. So our plane of interest is the Z front, and it's moving in the 2 direction. And obviously it's linked to this. So what it means that as the system is deforming in this point, this direction will be what we have. So, and of course, we need to think also about our boundary conditions. So because this is a YZ kind of loading, so the 2 boundary conditions that we will need, so will be the Y and the Z. So I'm going to suppress this. So Y will be the first one. So we're working on YZ. So Y will be what we need. So what will be the degrees of freedom of Y? So 1 and 3 will be fine, because the system needs to move in the Y direction. Okay, so the top end needs to move in the Y direction. And then we'll just need to create the Z base back. Okay, so the Z back boundary condition will be the second one. So what would that mean? It will be on the back, the Z back. And because there's a commonality around here, so and we want this top to move in the Z direction, so 2 and 3 will be what we want. So if we just think about what we have done, so based on the load, YZ load, so this YZ load is acting on the top, so moving the system in the 2 direction, sorry, in the 3 direction. And then the other one is acting in this Y direction, moving the strong face in the Y direction. Okay, so we need to have this to be free to move and that to be free to move, and then it works very well. So that's the only change you need to make to create what we have. So if we then go and create a copy based on that same model, so we can then say this is ZX shear. Okay, so with the ZX shear, we'll do the same thing, come back to the boundary condition. So the 2 loads, the first load, we rename that as ZX load, and then the other one will be XZ load. Okay, so these are the 2 components of the shear stress. So ZX load, which is this one, is linked to this. So it's going to move in the 1 direction, ZX, so X being the 1 direction. Okay, so we know that it's moving in this 1 direction. It will be linked to the Z plane. So what do we do? So let's go to the constraint equation. Obviously we know, so ZX, so we're going to move this to the front in the 1 direction, and it's linked to that, and this is fine. So that's why ZX, Z for the face and X the direction of interest. So that's what we were. So the load here is translated effectively here. So what about the XZ load? So the XZ load would have to move onto the Z direction, Z axis, because it's X in the Z direction. Okay, so we now have it in this X direction, ZX. So, and we then need to link it to the X face. So it's got to be linked to the X face because it's XZ, so X normal face. So the second constraint equation will be to the X front face, but in the Z direction, which is XZ. So again, we've got those 2 planes of interest. two planes. So that means the back planes of the Z and the Y, the Z and the X will be important. So we've got the Z. I'm going to suppress the Y, and then I'm going to activate the X. So that means the X and the Z will be the boundary condition of interest, because they are the faces that are constraining on the system. So let's just make sure we have it correctly looking. So for the Z back, so what is happening that this system needs to move in the X direction, the Z direction. So it will have to be free to move in the Z direction. So our boundary condition will be 1 and 2, and we'll leave this one free. Now, what about the X back? So we've got this X back, and what is happening with the X back is that this system is going to have to move with respect to this case. So it needs to be free to move in the one direction, so which is correct. So we leave it, and then 2 and 3 will be fine. So that way, again, the common line in the back here will be a line where this whole system is anchored, and everything will work very well. So we can then go and create the jobs. Okay, now we've got the job. Simply we'll submit it and we'll look at the result. Okay, so we finished the result, and here's the result we getting. And this is basically based on the XY shear loading. So if we look at the result we get, okay, so that's what we get. And then we just need to animate it a bit just to get a sense of what it's doing. So, and this gives us some really interesting result. So as the system is shearing in this direction, it's also being sheared in that direction. And we've got a dominant shear plane right in the middle there. So if we change this to shear stress in the 1-2 plane, so, and probably look at the strain involved. So look at the strain on the 1-2 plane. So it does show you there's a dominant shear, quite a lot of significant shear deformation around that region, which does prove to the fact that the system is going to go in a perfect pure shear behavior. So if we then look at the comparison between the two, so if you look at the perfect side view, so what you see is that this front end is being deformed, and the top end there is also being deformed, and everything looks perfectly okay. So that's a lovely pure shear deformation that you can see on a system like this. So we're going to then look at the next case, which is the YZ shear. So again, this is what you get with the YZ shear. So a similar kind of behavior like the previous one. So the system this time around is being sheared in this direction and sheared in that direction. And you have again a clear picture of what's going on. So if you look at the shear strain, and especially on the YZ, which is the 2-3, again, it does point out to this dominant shear a lot of shear deformation around this region. So obviously there is a region of weakness within the structure, and this is why you're getting this, because the reinforcements of the microspheres are not as strong in that region, and so there's a dominant of shear deformation at that point. So let's look at the third one, which is the ZX shear. So again, a similar kind of behavior as the previous one, just the system shearing in the front, and then you can see a distortion of that microsphere. So very interesting results. So if you look at the shear on the 1-3 plane, and it does show you again some interesting distortion around that region. So very interesting results that you're getting depending on the shear deformation. But clearly what we want to do is to get the stress strain data based on this. So if we go into the create data, so the history output, so remember we're interested in deformation in the Y direction and the X direction. So let's look at the reference point 1 data. So this is the reference point 1. We're looking at the reaction force in the 1 and the displacement. So I'll press down shift control and then go to the same. So basically we're tracking what's happening in the Y direction of reference point 1 and the Y direction of reference point 1. So we plot that and we get some really lovely graph that comes there. So we'll just extract that. So ABAQUS plugins, tools, Excel utility from this current plot. I've already prepared an Excel spreadsheet that contains an analysis for you to work on this. So please do download it again from the description section of this video, which will show you how to go about doing this. When we export that data, this is sort of what you see. So I'll just Control A to select and Control C to copy. So and this is my Excel spreadsheet that I've already formatted. So I'm going to paste the first data around there. And we now go over to the same code again. Remember, there are two measures that we want. So we go back here. This time we're looking at what's the deformation on the top in the X direction. So that means reference point 2, but in the X direction. So reaction force reference point 2 and reaction force reference point 2 in displacement reference point 2 in the 2 directions. So those are the two key things we want to track. And then we'll plot that. And then we get a data that looks like what we had before. So plugin tools, Excel utility, that fine. So again, like we did before, copy, Control A to select all, Control C to copy. And back onto here, this time around, we are imposing that on the second case. So there are a few things that we are missing here, and that is the surface areas of the X front face and the Y top face, because we need them to calculate. So if we go back to ABAQUS, so you see that the surface area here is an irregular surface area. So there's something going on here. So if you just go back onto the assembly module, so we need to probe. So we want to probe, let's say just a point here. So on the surface, and then we get the coordinate position, so we just select that. So I've already written a Python script for helping you calculate this surface area. So, and that's what the Python script. So the data that we've probed and copied, so that's the coordinate position. I paste it here for the X front face. So this is our model name, XY share, and this is our path name from the model. So we just select Control Alt select all, and then go back here within the kernel command. We can run that. So when you run it, it will now give you the value of the surface area of that face of interest, so that we can then go back to here and paste it for the X surface. So this is the first surface that we wanted to work, and once you put in the programs and everything works out. So the next thing is the Y top. So again, with the Y top, we can probe as well. So let's say we probe somewhere there on the top and click done. So it gives us again the coordinate for the Y top. So we'll select that, and then go back to the Python script, and then I'll just replace it with a new point of interest, and it works. Control A to select all, Control C to copy. Then back in Excel, back into MATLAB, into ABAQUS, I will just, so again, we've got a value that shows us what's happening, so that we can put back into this space. So you can see they are all different, and once you put that in, and in there the dimensions are given, so the areas are correct, and we've got the plot that shows us what's happening in terms of the first one being the stress strain data of the YX. Remember, with the YXY share, you're looking at the Y displacement values, and then the XY share, you're looking at the X displacement values, which is what you have here. And then you put that in and you get that. So that gives us a measure of the stress strain data for the two cases. If the system is homogeneous and everything is working well, then they will be right on top of each other, no difference. Because we are looking at something that's got like a heterogeneous media within it, and it's a syntactic foam, there is a little bit of deviation between them. However, in terms of effective properties, what we're interested in will be the average of the elastic response and the average of the yield for this material. So that's why the next thing I did here was to get the average of the slope for this case plus the slope for that case. Again, if everything is perfect, those two numbers will be exactly equal. But for our purposes here, I decided to just get the average of what the slope is and slope would be, which sort of represents, the effective Young's shear modulus in this case. So this would be the shear modulus. In terms of strength, again, a similar thing. I just found the maximum of that and maximum of that and get the average, and that's sort of what you will get for that. So I did the same for the YZ plane. Open the YZ plane, extract the data, and you get a response with the second data, which is the ZY being slightly higher. So the Z direction seems to be giving you a bigger value. And the reason why is that if you go back to this model, you see in the Z face, the area is much smaller. So there's a much smaller area in the Z phase. And so, you're dividing the reaction force with a smaller area, and that will normally give you a higher value. And that's what we are getting on this case. So you look at the ZX, a similar thing would happen with this one being again slightly bigger, this one being the ZX. And then the final thing I did was to try and make some comparisons on that. So if you look at the comparison, the first thing you will see, okay, so for all the XY or YX share, so these are the black ones. The ones that are red are the ones that are the YZ and ZY. And then the ZX and XZ is the ones that are blue. So we see some sort of repeatability in what's happening in the off-plane directions, as well as the in-plane directions. Although in the pursuit behavior, there's slightly a variation, a difference in the XY and YZ plane. But however, the behavior is really very interesting based on what you can see. Then I went on to look at the effective Young's modulus, which is the shear modulus for this, and they are all sort of comparable, and their strengths are all sort of comparable. Please do subscribe to this channel if you've not already done so, and please do leave me a comment within the comment section of this video of what is your wow moment in everything that I've shared in this video. Maybe there is something that you've never learned before that really interested you. I want to hear about it. And if you have ideas around a new video type or a new concept within this area that you want me to push and explore, I'll be happy to consider that so that I can make a video to to help you. So what I've done here is to show you how you can undertake a pure shear deformation of a syntactic foam. So if you really want to see how this system will behave in terms of its tensile behavior, then this is the video to look at. Or in terms of this compressive behavior, this is the video to look at. Thank you for your interest in this video, and I'll see you in the next. Bye-bye.